name is Ralf Behr. I'm a scientist at PTB, and I'd like to introduce you to our Programmable Josephson Voltage Standard, and that's the basis for our AC quantum voltmeter doing differential sampling. That will be the first step I will show you, and the second one is the subsampling procedure up to 100 kilohertz. Behind me you can see our system. So we have the programmable Josephson array chip down here in the helium diode, in this cryoprobe. All the segments of the cryoprobe are biased by this fast bias source, and we are using the synthesizer, 70 GHz synthesizer, which is locked to our 10 MHz atomic clock to provide the microwave frequencies. Then we have, so the output is going here to this PXI system, and now I will show you how we usually start with this. So here we have two programs. I'm going with these programs now manually. Usually we can also run automatic measurements, but in this case I'm going slowly through it. So the first is usually to apply an AC waveform. I'm going to a sine wave using 20 samples at a frequency of 1000 Hertz, and I apply this, and I shouldn't forget to switch on the microwave power, which is controlled by this button. Okay, now the microwave is on, the signal has been sent. What I have to do now is to put a short here first. So I'm just sending the stepwise Josephson waveform to the PXI to check if everything is fine with the system. I'm using our program for differential sampling and differential subsampling. I have to give the sample rate, the expected frequency, which I programmed to the PJVS. Then I have to select the proper waveform, because this program has to know what are the Josephson voltage steps we are using now. So I selected 20 steps and 1 volt RMS, and then I can start the reading of the PXI. And what you see here now is the Josephson waveform, and I can go to check steps, and as you see here, okay, there are little disturbances, but the difference between the measured steps and the calculated steps are all around 0, so everything is perfect. I can do a reading, and as you see, there's a stable reading. The theoretical value for the RMS of the Josephson should be 1 volt and 91 microvolt above, and that's exactly what we measure now. So that means the gain of the PXI is also set properly. Because the PXI is a sigma delta ADC, so it's coming with ringing, and of course what is important, because the Josephson is not, so the signal with the transients, we have to cut out the transients to make a proper reading for this. And in this case we are already taking out 50 points on each side to get rid of this ringing. So if I don't do it, what you immediately can see is ringing at the edges before and after the transients, and of course the reading is completely spoiled. The idea is now that we want to measure a sine wave, and we have got two different generators here. I will use the Luke calibrator on the right side, and I will start with the 1 kilohertz signal. So instead of putting the short for testing the system, I am now connecting the cable of 1 kilohertz. I have to set up the generator here. So I'm going for 1 kilohertz, and the complete system is synchronized starting from the bias source. The bias source is sending the clock and the trigger signal to the PXI, so the PXI is synchronized, and then it's forwarded to to this little synthesizer here, which then is in the burst mode, gives the proper triggering to the calibrator. So I also have to put this to 1 kilohertz. It's in the burst mode, so I can operate this instrument and have to go on phase lock. Yes. Push the trigger once, and then I should see the differential signal here. This is now the differential signal, and we can see the recombined sine wave based on the Josephson steps. I'm still not deleting the transients, and what you see there are many spikes. So I have to delete these transients, and then I'm going to have a proper differential signal and a proper sine wave, which then is used for the readings. I can start this measurement. Okay, now you can see we are now taking the readings of the RMS value for quite a long time. You can see that within the noise the signal is constant. Usually in this program we have an Allen deviation analysis to show that we can now, with this calibrator, we can go down to a few parts in 10 to 7, and this level depends on the noise level of the calibrator. So this is a measurement of 1 kilohertz with the differential sampling, and what I will show you now is I will now move on to subsampling. Okay, we are now going to the subsampling, and the idea is to run the Josephson much smaller and to go with quantized steps through a high frequency waveform to have more flexibility to increase this waveform. Because the Josephson is running much slower, we are able to cut out transients and to rely on differential measurements at zero. So what I have to do now is I'm reprogramming the Josephson. I'm using a triangular waveform to have a linear distribution over the complete amplitude. I'm increasing the number of Josephson steps I'm using for this waveform to have a better resolution, and I'm reducing the basis frequency of the Josephson now from 1 kilohertz to only to 20 hertz, and I can send this waveform. In this manual program I have to tell the program, okay, now the basis for our measurement is a different file. It's 40 steps, 20 hertz. That's also what I have to tell my system here. So I'm going here to 20 hertz. I'm telling I have 40 steps per period. I now can increase the number of delete ringing points because we are working at a very low frequency. And most important, I should click here on undersampling. Then, if I'm doing undersampling, I have to tell the system what is the high frequency that I want to measure, because now the Josephson is running very slowly on 20 Hz, but my calibrator is still on 1 kHz, so I have to give here 1 kHz into the program, and then I can start this measurement. And as you see, now this is a combination, so I'm adding the triangular waveform from the Josephson, and you see how the high frequency is passing all these quantized steps. Because everything is properly timed and triggered, I can recombine it to a sine wave measurement, and as you see as before, so that this was a differential measurement, and now I'm going to subsampling, and there's no change in the value, which shouldn't appear because we are measuring the same generator at the same frequency and the same voltage output, 1 volt. once this is set up, it's very easy now to go to a higher frequency. I just have to reprogram the calibrator to going up to 100 kilohertz, and that's what I do. So I stop this program, I set 100 kilohertz to this calibrator. I also have to reprogram this little synthesizer here, also work at 100 kilohertz. And then I can start and lock the frequency. And the only thing I have to do now on this program is to tell the program, okay, I changed this frequency now to 100 kilohertz. And start it, and I will clear up this graph now. And you see now, you still see these 40 steps of the Josephson here, but the picture is much more colored because we have many more high frequency periods crossing each step. The system is running in a similar way. Now we are recording the RMS value of this, and what is important here to mention is because now we are going to a very high frequency, we have to consider the input filter and the cable correction. And to consider the input filter correction, I have to click on this button here, which means all our measured data are immediately corrected by this filter function of the PXI, and I have the proper reading for this. This hasn't been done now, so if I click on this button now, there's a correction, and you see how this program is changing the value, and this value also contains some cable correction, but this is something which comes afterwards. And I can now do a longer measurement. Of course, due to this subsampling, because we are throwing away many more data, the uncertainty is higher, so the standard deviation of the readings is higher, and we have to take readings for a slightly longer time. Okay, now the measurement time is just 70 seconds, and if I run the ln deviation measure, you see the ln deviation is even going below 10 to minus 6. Applause.